Sir, shall we start? Good afternoon to all the participants. Sir, do you hear me? Hello, sir.
Yeah. Yes. Yeah.
Yes, sir. Okay. Sir, welcome back for the second day of this 3-day FDP. So yesterday's section on foundations of the quantum computation provides us with a profound insights into the fields of core principles, various core principles, in mechanics, computation, and algorithms. Uh, and it is an honor. It is my absolute honor to welcome Professor R. Shankar Narayanan, sir, a leading expert in the quantum computation, for today's session. With over 25, more than 25 years of experience and more than 6 high publications to his credits, sir brings immense expertise. Invite all the participants. For all Richard, the participants are there. You should engage fully session. Around 200, more than 200 participants, including YouTube channel, joined. That is almost 40% only responded, joined in this FDP. So participants also requested to raise your hand after the end of, at the end of the session to ask your queries, because chat box is not working properly. So you can raise your hands at the end of the session. The resource person, Professor Shankar Narayanan sir, will clarify your doubts at the end of the session, definitely. So now I request my colleague Sri L. Nagesrao sir to formally introduce our esteemed resource person, Dr. R. Shankar Narayanan sir, to the audience. And Elena sir, please take the session to introduce our resource person.
Yes, sir. Thank you. Resource person Dr. R. Shankar Narayanan sir. Dr. R. Shankar Narayanan sir is a professor in the Department of Physics at the National Institute of Technology. With research conducted at the Physical Research Laboratory, PRL, Ahmedabad. Dr. Shankar Narayanan earned his BSc in Physics in 1992 from St. John's College, Tirunelveli, affiliated with Madurai Kamaraj University, Tamil Nadu. He completed his MSc in Physics in 1994 from MDT Hindu College, Tirunelveli, under MS University, Tamil Nadu. Professional experience. He started as a postdoctoral fellow at the Physical Research Laboratory, Ahmedabad, from January 2002 to September 2002. Later, he was a postdoctoral fellow at Weizmann Institute of Science, Rehovot, Israel, October 2002 to November 2003. From November 2003 to April 2006, he served as research at the School of Physics. Bharathidasan University, Tiruchirappalli. He joined NIT Tiruchi as a assistant professor in April 2006 until March 2018, associate professor in March 2008 until March 2024, and has been professor 24. Research interest. His research focus on Hamiltonian systems, chaotic quantum systems, quantum information and its applications, chemical kinetics, and physics education. Courses taught. At the undergraduate level, BTech across engineering branches, he teaches physics. For postgraduate MSc Physics, he covers mathematical physics, electromagnetic theory, statistical mechanics, numerical and computational methods, and quantum computation, quantum information. He also teaches mechanics and thermal statistical physics to BSc, BEd physics students. Research guidance. Dr. R. Shankar Narayanan has supervised 28 MSc Physics projects and 24 MTech NDT projects. He has guided 5 PhD scholars to completion and currently supervised 2 more. Publications and contributions. He has authored 45 research papers, including 34 in journals and 11 at conferences. Additionally, he has given 44 invited lectures and led 31 physics demonstration sessions for about 2,500 school students using custom designed experimental models. Thank you, sir. Now I'm handovering the session to Dr. C. Chanjanelu, sir, remaining.
Thank you, sir. Thank you very much. my colleague L. Nageswara give insightful introduction about Professor Shankar Narayan sir. I will now hand the session to our esteemed resource person, Professor R. Shankar Narayan. Welcome, sir. Please take the session.
Okay. Am I audible, sir? Good afternoon.
Yes, sir.
Yes, sir. Yes, sir. Audible, sir. Audible and visible, sir.
Okay. Yeah, thank you.
you.
Yeah. See, first of all, it is my honor and privilege to be part of this faculty development program organized by the Department of Physics, Bapatla Engineering College, Bapatla. I congratulate all of my colleagues in the college from the physics department having arranged such a wonderful program, and I'm also honored to be part of it as a speaker. And the faculty, I also thank, I immensely thank the respected principal of the college, and particularly my sincere thanks to Dr. Aruna, convener, and the Dr. Sambasayara, co-convener, and all other faculty colleagues for having coordinated this program with a very special care and attention. So it is indeed a great gathering that, though we are spatially separated, we have an opportunity to interact through online. So it is a wonderful opportunity, and I hope this session will make some benefit to people, and in turn, not only the participants. If I believe that, I strongly believe that I will also be immensely benefited from the interaction from the fellow participants. So faculty development program is a very, very important activity for every faculty of the college. And this is the occasion where we share our ideas and interact the vast scientific domains, and we can also clarify our doubts, and we can also enhance our knowledge in the other domain in which we may or may not have the deeper understanding. And our understanding and our enhancement of knowledge directly helps to hundreds and thousands of students we meet over our career. So there is a saying which says that a teacher is a teacher if he is a student. So the idea is that if we are a teacher, we should learn like a student. So in this faculty development program, I see that I myself as a student and interact with people, and I learn from others. And so is the case for all the participants who have actively participated in this program. Yeah, I think all of you have listened to the yesterday's presentation by Dr. Balakrishnan, who has given an introductory talk on quantum mechanics and the evolution of science, which led to the idea of quantum mechanics.
Yes, sir.
So, is my slides visible to all of you?
Yes, sir.
Yes, sir.
Okay. I'm trying to put it in full screen mode.
Yes, sir.
Is it fine?
It is okay. Now it is okay.
Okay, yeah, thank you so much. So the yesterday's talk was a very introductory level, and it was giving a probably historical view of how the subject of quantum mechanics has been developed over the last many decades. So as we all know, the modern scientific pursuit was genuinely started by Galileo Galilei, as Dr. Balakrishnan was pointing out yesterday. And since then, there are so much of activities in understanding the nature and so on. So in this pursuit, I would say that the most beautiful, mathematical theory which people have ever devised is the quantum mechanics. And even though it is so beautiful, parallelly it also has its own. We also have sometimes difficulty in understanding the subject for various reasons, because we are all living in the classical world or macroscopic world, right? So here is a subject which actually talks about or trying to understand the atoms, their shape, the stability, and so on and so forth. So definitely it is going to be somewhat weird kind of thing because we never see atoms and so on. So in that sense, quantum mechanics is definitely a strange subject by itself. And if you do not understand quantum mechanics in the first reading, you don't have to worry about it because you are not alone in this on this earth. Okay, there are so many people who don't completely understand. So, but the kind of ideas which is put forward in the development of quantum mechanics and the kind of the number of experiments which has justified our understanding of atomic phenomena was immense, and so we have to learn and appreciate the quantum mechanics from at any cost. And so our understanding and our clarity will directly reflect on our teaching and so to the younger generations. So here is a subject called the quantum computation, and the subject of this faculty development program is the quantum technologies, emerging trends in physics and computation. So here is a subject called quantum computation, which actually merges the ideas of quantum mechanics and the ideas of computer science. So there is a beautiful merging of physics and computer science. So a lot of inspiration from physics people, a lot of inspiration from computer science people, and a lot of inspiration from other engineering branches people, and so on. So it is in a sense a multidisciplinary subject wherein people from different expertise, they come together and try to develop the subject. Okay. And of course, we need to we have to have a good flair of mathematics so that we can take this subject, we can appreciate the subject and take the subject forward. Okay. Right. So the title of my talk is Quantum Mechanics, Computation, and Algorithm. I'll be talking about these three aspects from the quantum computing point of view. And I should say that United Nations has announced 2025 as the International Year of Quantum Science and Technology. So it has been 100 years. The idea of this International Year of Quantum Science and Technology 2025 is to commemorate the 100 years of the formal development of quantum mechanics, which was the foundation was laid by Erwin Schrödinger, who wrote his famous equation in 1925. So it has been 100 years, and still we are celebrating this quantum mechanics, and we are trying to look at the new possibilities in for the benefit of the humankind from the principles which govern the the motion and dynamics of the atoms. Okay, atoms and molecules. So my outline of the talk is something like this. So I'm going to talk about okay, this talk is broadly divided into 5 topics. The first one is the quantum mechanics, where I will discuss the mathematics required to understand the quantum mechanics, the basic mathematics which is required to understand the quantum mechanics. And the second note is on the inspiration from the computer science. And the third and fourth are the fundamental building blocks of computation, which is qubits and gates. So here again, we have some of the algorithms, how one can develop algorithm to solve certain problems, and those algorithms, how they are going to be more efficient than the conventional algorithms using and this is going to be a kind of demonstration to see how quantum mechanical principles are overpowering the classical algorithms which we know till now. So let us start with a few important topics of fundamental topics of quantum mechanics. As Albert Einstein says, the quantum mechanics is a real black magic calculus. We have to learn this algebra and calculus, patiently, so that we can contribute to the subject of quantum computation in the days to come. And of course, all over the globe, there are a lot of interest on this subject. And India is also now hoping to make a big contribution. And government is also encouraging in all possible way. So the idea is actually to refresh the basics required for the quantum mechanics. So before we really get into quantum mechanics and the applications of quantum mechanics from the computational point of view, we need to understand some of the basic postulates. The first postulate is the state. And the second one is the observable. Third one is the measurement. And fourth one is the dynamics. Okay. So there are four postulates upon which the quantum mechanics has been built very carefully and systematically. So when you say state, classically, we talk about the subject of we know that mechanics is the heart of the physics. That is where the modern scientific pursuit has starting from Galileo and Newton and so on. So when we talk about a state of a system, we say that from mechanics point of view, if you know the position of a particle and momentum of a particle at an instant of time, we say that we know the state of a system. Right? If you know the position and momentum precisely at a given instant of time, we say that we know the state of a system. That is how the subject of mechanics has been developed. Mechanics, or what we call the classical mechanics. And similarly, we also have observables. When you say observables, anything which you measure in the laboratory, it could be position of a particle, it could be a momentum of a particle, velocity or momentum of a particle, it could be energy of a particle, and so on and so forth. So all these quantities are observable. So these observables are going to be the fundamental quantity in our investigation. How these observables change with time and so on and so forth. And third one is the measurement. So measurement is basically in the laboratory, we make measurement, right? So you measure the distance, you measure the velocity, you measure the acceleration, right? So these are the concepts in mechanics. And the last one is actually the dynamics. So dynamics talks about the evolution, how this system changes its state. If you know the position, momentum, x and p at some instant of time t1, how do you predict the position and momentum at later time t2? So x at t1 to x at t2 is what we say. Essentially, the object is undergoing a evolution or dynamics. So we describe this evolution of dynamics from the classical point of view using the Newton's law of motion and so on and so forth. So all these ideas, we are going to take it forward in the domain of quantum mechanics, but from a completely different perspective. Okay. In quantum mechanics, we do not have the notion of position clear. We do not have the notion of momentum in the sense of classical mechanics. What all we have is called the wave function. So we will be defining the state, observable, measurement, dynamics, everything in terms of what is called the wave function or state vector. Okay. So let us see how to define a state of a system from the quantum mechanical perspective. Yes. See, quantum mechanically, state is a complete description of an isolated physical system. What do you mean by isolated system? A system, when you say system could be a one particle or one atom or few number of atoms or something. Okay. So that is a physical system. Isolated means the system under consideration or the system of our interest is not interacting with the rest of the world. So that is called the isolated system. So this is for the convenience we say, because it is very difficult to understand the interaction between the system and the environment. So for simplicity, we say that system is not interacting with the environment. So we consider the system as an isolated physical system. And so this isolated physical system is being described by the state of such a system is described by a ray or vector in a space called Hilbert space. So what is Hilbert space? Hilbert space is a space in which we are going to define the state of a system quantum mechanically. Okay, so in the classical mechanics, we talk about the vector space. In the vector space, we mentioned that we define the position, momentum, and so on, right? So when you define position, momentum in the classical mechanics, we also define what is called the phase space. X-axis, you take it as a position, Y-axis, you take it as a momentum, then that space is actually called as a phase space. So phase space, we call it as a state space. A point in the phase space, we call it as a state of a system at some instant of time. So in analogy to that phase space, called the Hilbert space. Unlike the phase space, which is a real space or a real vector space, here we have a complex vector. Here we have a Hilbert space, which is a complex vector space. In this complex vector space, we are going to define a state of a system by what is called the complex vector or a ray. So which is denoted by ket psi. So the ket psi is a notation given by the Paul Dirac for the convenience. There is nothing religious about it, nothing spurious about it. It's just a symbol. It's just a function. Okay. It's an abstract representation of a state. Okay. So when you have a state psi, I can always give a representation to the state psi. If I give a position representation to this state psi, I will write the same state as a psi of x. So here I'm giving a x representation of the state psi. Okay. Similarly, I can give any representation. So psi is basically a mathematical complex abstract object. And for every state vector psi, you have a complex conjugate pair, which is actually again, this is actually another psi. So this is called the ket psi, and this one is called as the bra psi. Okay. So these two notations are denoted by introduced by Paul Dirac. It's called the bra and ket notation. Combinedly, we call it as a bracket notation. There is a mysterious about it. It's just a way of writing the object in a compact way. Okay. Either you can write psi in this way, or you can write the psi in this way. So if it is a one-dimensional, if you're talking about a system which is moving along x-axis, you can write psi as a function of x. If you are going to represent this state vector of an object which is moving in a three-dimensional space, psi will be a function of x, y, z, and so on. Okay, right. Now, having defined the state vector or ray, we have to, this Hilbert space, we have to work with the Hilbert space, and we have to define certain mathematical operations to be done on this vector psi. Suppose you have two states, psi and phi. Then we take what is called the inner product. So the inner product here is defined as ket psi multiplied by bra phi. So this notation is equivalent to this integration. So essentially, this simple notation is equal to this object, this quantity, integration of phi star of x into psi of x into dx. So this the entire integration is just being represented by this simple quantity, this simple notation. Okay. So the inner product is something like the dot product in our real vectors a and b. Then you define a dot b, and so you have in the real vector space you define the dot product. Something similar to that fashion, we define what is called the inner product of two vectors psi and phi in this way. And we also have this inner product such that psi is a positive quality, and this inner product obeys what is called the linearity. So which means that if I have a state C1 psi 1 plus C2 psi 2, where C1 C2 are some complex numbers, and if I take an inner product with another state phi, then this object is equal to C1 phi psi 1 plus C2 phi psi 2, where C1 C2 are constants. So this property is what we call as a linearity property, and so this space is actually called as a linear complex vector space. Okay, they obey this linearity. And we also have a property called skew symmetry, which means in the inner product of phi and psi is equal to the complex conjugate of inner product of psi and phi. Okay. So we proceed further by defining what is called the norm norm of a state or a vector psi is represented by psi with a 2 vertical line on either side, which is nothing but square root of the inner product size. Okay, square root of inner product of psi psi. And we also make sure that this psi psi is equal to 1. If psi psi is equal to 1, we say that the vector psi has a unit norm. Even if the given state is not, the inner product is not 1, you can always rescale it such that the state can be can have a unit norm. If it has a unit norm, we say that the wave function or the vector, the wave vector psi is a normalized ray or normalized vector. Okay. So this is called the normalization. So this normalization leads to a very beautiful physical interpretation due to Max Born. Okay. So it is because of this normalization we associate effects. So if you have a psi of x, then this psi of x dx is actually a quantity which is supposed to be the probability of finding a particle between the position x and x plus dx. So this interpretation comes because of the fact that we introduce what is called the normalization condition. This is called the normalization condition. Okay. So in quantum mechanics, the state psi and this state, the psi multiplied by e power I alpha, where alpha is a constant. So these two states are physically same. We do not differentiate this state and this state because this factor is just a multiplicative factor. So this multiplicative factor is not going to physically affect the state of a system. Okay. So this alpha, we call it as a global phase factor, which is insignificant from the quantum mechanical point of view. On the other hand, suppose we have two states, phi 1 and phi 2, the quantum mechanics actually permits what is called the principle of superposition. Because the vector space is a linear vector space, it admits what is called the principle of superposition. That means if phi 1 and phi 2 are two possible states of a system, then C1 phi 1 plus C2 phi 2, which I call it as a state psi, is also a possible another state of the same system. I repeat, if phi 1 and phi 2 are two states of a system, then C1 psi 1, C1 phi 1 plus C2 phi 2 is also another possible state of a system. So this is what we call as a principle of superposition, which is one of the fundamental hallmark of linear vector space and so for the quantum mechanics. Okay. Now suppose I take a state psi defined in this way, and I take another state psi prime, which is C1 phi 1 plus C2 e power I beta phi 2. And you will see that these two states, psi and psi prime, they are distinctly different in the Hilbert space. Okay, unlike the earlier case. So here, that is because of the reason that there is a phase factor which is sitting at only one of the term. Unlike this case, e power I alpha is multiplied with the whole state psi, but here e power I beta is multiplied with one of the terms in the psi prime. And so psi prime is physically different from the state psi. Okay, so state psi and psi prime are distinct physical states. Okay, and this factor, phase factor, beta, is sometimes called as a relative phase factor, which cannot be ignored in your calculation. Is it fine so far?
Okay, sir.
Okay.
Yes, sir.
Okay, now we come to the idea of the observables. So observable is nothing but a property of a physical system that can be measured. The examples are, as I mentioned earlier, position, linear momentum, angular momentum, energy, velocity. I mean, velocity and momentum are same. So momentum, angular momentum, energy, and so on. In quantum mechanics, every observable can be thought of as a linear operator. Okay, this is something very important. For every observable, there is an equivalent operator in quantum mechanics. Suppose you have an observable A. Then associated to the observable A, there is an operator A. Okay. There's an operator A. Okay. Now, suppose I have a state psi which represents the state of a system at some instant of time t, then I say that this operator operates on the state psi, and that is going to give me that is going to change the state from psi to psi prime. Okay, so A is an operator associated to an observable A, and this operates on state psi, that gives me a new state psi prime. Okay, so this is the idea of observable in the language of quantum mechanics, and this observable is such that it obeys the linearity property. What do you mean by that? As we mentioned earlier, if you have an operator A which operates on C1 phi psi 1 plus C2 psi 2, then the resultant one is C1A psi 1 plus C2A psi 2. Right? So this is the linearity property. So this operator has to obey it should be a linear operator. And we should also have the inner product rule. Suppose I have an inner product of phi with psi prime, and psi prime is nothing but a psi, as mentioned earlier. So I take inner product of phi with psi prime, which is phi a psi. So the meaning of phi a psi is nothing but this integration, nothing but the inner product of phi and psi prime. Okay, prime. Okay, it's just a compact way of writing this whole integration as phi a psi. Okay, and again, we are going to define what is called the adjoint A dagger. So what it says that for every operator A, there exists an operator A dagger such that this object is equal to this object. Okay. So this linearity of the vector space ensures that for every operator A, there exists an operator called A dagger. That A dagger is called as adjoint of A. So there exists a dagger such that this quantity is equal to this quantity. In quantum mechanics, we will be frequently using what is called the self-adjoint operator, which means A and A dagger are one and the same. So if you find a dagger of A dagger for a given A, that is same as A itself. So A is equal to A dagger, and such an operator is called as a self-adjoint operator or Hermitian operator. And these Hermitian operators play a very, very crucial and fundamental role in the formal development of quantum mechanics. All the observables we handle, they're all real, right? So associated value equation. Suppose I have an operator A. The operator A operates on some state, I call it n. You can write whichever notation you want. I just put ket n. Okay. A operates on n. In general, I should get some state n prime, right? If suppose A operates on n, gives me the same state, n itself, multiplied by a number. It is a scalar. Please understand the difference in this equation. A is an operator and an is a number. If A operates on n, gives you the same state n multiplied by a number, and this equation is called as the eigenvalue equation associated to the operator A. Okay. And these real numbers this number an is called as the eigenvalue, and these states are called as the eigenfunctions or eigenstates associated to the operator A. And this equation is called as the eigenvalue equation. Okay. So these states, the eigenstates are such that the inner product of two different states is nothing but this. So delta m. What does it mean? If m is equal to 1, we get 1 as per the normalization. If m is not equal to n, this result will be 0. So such states are called as the orthonormal states. Okay, orthonormal states. Okay, so this is nothing but orthonormal condition. What we just wrote is an orthonormal condition of the eigenstates of a Hermitian operator. Okay, and this set of n. By the way, you can have many number of states and many number of eigenstates and many number of eigenvalues for a given operator. Okay, Now, if you take all these eigenfunctions, and this is the spectral decomposition of a given operator A. Okay, so if you know the eigenvalues and eigenfunctions of an operator A, the operator A itself can be written down in terms of an and the an and the n. Okay, and this particular object is sometimes called as the projector operator Pn. I will come to the important significance of projector operator in the next slide. So why these eigenfunctions are important? So these set of eigenfunctions, they span the entire Hilbert space. If you have a set of, capital n such eigenfunctions, these n such eigenfunctions will form a n-dimensional Hilbert space. So you define a Hilbert space in terms of a set of eigenstates of some Hermitian operator. In that Hilbert space, you are going to represent the state, any arbitrary state of a system. So if you have defined the Hilbert space, if the Hilbert space is spanned by a set of eigenfunctions, then any arbitrary quantum state of a system can be written down like this. Okay. So this is nothing but your wave function, which is supposed to have all the information about the particle of your interest. And this state psi can be written down as a summation over Cn, where Cn could be any arbitrary complex numbers, and n is the eigenstate of the observable you have in your mind, okay, or any Hermitian operator, for that matter. So here Cn is nothing but n psi, the inner product of n with psi, okay. Because of this orthogonality property, we can easily see that Cn is nothing but n psi, right? And this Cn are such that sum over n Cn mod square is equal to 1. Again, this equation ensures that it is a normalized, this wave function is a normalized one. Normalized means the norm of the vector psi is 1. Okay. Is it fine so far?
Yes, sir. Very good.
Okay, thank you.
Yes, sir. It's fine.
Okay. So now next we come to the another postulate which concerns with the measurement postulate. So in the measurement, we are associating the meaning for the eigenfunction and eigenvalue which I just mentioned. So I said an is the eigenvalue of an or the eigenvalues, and ket n are the eigenstates of an observable A. So what is the meaning of this quantity? So an is nothing but the numerical outcome of a measurement of the observable A. You have an observable A, right? Now let's say that the state of a quantum state of a system is given by psi, right? Now you want to measure the observable A when the system is in the state psi. Okay, so when you make a measurement, you will get some outcome. So the set of outcomes are nothing but the eigenvalues. The set of outcomes are nothing but the eigenvalues. Okay. And this state, ket n, are nothing but the state of the system after the measurement. So the point is that before the measurement, the state of the system is psi, and after the measurement, the state of the system will be one of the eigenstate n. Is it clear? And an is the numerical outcome of a measurement of the observable A. Okay. So that's what I mentioned here. Now, if psi is a quantum state and outcome is an is obtained, then we are associating a probability for the outcome. An is actually an outcome, and an is obtained with a probability. Okay. So an can be obtained with certain probability. That probability is nothing but P of an. So how do we define this P of an? P of an is nothing but this quantity, psi Pn n. What is Pn? Pn is nothing but this quantity, n. This outer product. This is actually called as the outer product, and this one is called as the inner product. Okay. So psi Pn n, which is nothing but psi n psi, which is equal to n psi mod square. So what is n psi mod square? N psi mod square is nothing but the Cn mod square. So what you just saw, the Cn mod square, is nothing but the probability of getting the outcome AN in your measurement. Okay, so this is the meaning of the eigenvalue. Okay, and with this we can define what is called the expectation value of the operator or observable A. So if the state of a system is psi, and if the state of a quantum system is psi, and if you are going to make a measurement of the observable A on that state psi, then the quantity you are going to have is actually called as the expectation value. So the expectation value is actually defined as psi A psi, right? So what is psi A psi? Psi A psi is basically psi is actually given here, and psi is given here, right? Sum over n, c, and n, and A is actually sitting here, and this is actually the complex conjugate of psi. This is actually the ket psi, and this one is the complex conjugate, which is pra. Sum over m, c, m star. So the term within the first bracket is actually the complex conjugate of the term within the second bracket. So I'm just putting a different index m here and n here. So basically there are two summations here, which can be written down as sum over m comma n, cm star cn, an, mm. So since mn is nothing but the Kronecker delta mn, so this double summation actually reduces to single summation. Sum over n, cn. Evolution is unitary and so deterministic. What do you mean by that? Given a state psi 0, it is going to give you another definite state, deterministic state psi at later time t. Okay. So if the initial state is psi of t, the final state, so if the initial state is psi of 0, the final state is psi of t. So the state will be moving from point to place in the Hilbert space. Okay, so far I have discussed the 4 fundamental postulates of quantum mechanics. From here on, I'm going to take inspiration from computer science, and then finally we'll combine the idea of quantum mechanics and computer science to develop the qubits, gates, and finally I will, if time permits, I will discuss on 1 or 2 algorithms. So, do you have any questions at this point, or shall I move forward? Sir. Shall we take any questions now, or shall we take it later on?
Sir, some PK sir raised PNV Kishore raised the hand, sir.
Okay.
Can you are you?
Yeah, please. Yeah.
Sir.
Yes.
Kishore sir, are you audible? Sir, voice is audible to you, sir. Sir, do you have a question? You have raised the hand, sir. Sir.
Sir, we can take it at end of the session, sir. No problem.
Okay. Right. So now, yeah, now we'll move on to another domain called computer science. So what we have on our table is actually the modern computer, and this modern computer has got a lot of evolution. And so this modern computer is actually called as a Turing machine. There is a gentleman called Alan Turing who proposed this model of computer, and which has changed the way we have been doing the calculations. Okay, so in the computer science we have different models of computer. One is called the Turing machine, another one is called as a circuit model. So even the Turing machine is actually the idea. The most practical one is the circuit model, and the people who work in computer science, they also bother about the computational complexity. So basically, they want to identify. The computer scientists are usually it's a branch of mathematics. Okay, so these computer scientists, they want to identify and classify the problems which we want to solve. Okay, so broadly they classify the problems into easy and hard problems. Okay, so whatever problems. So this classification, this kind of studies comes under the domain of computational complexity. And so where do they classify this easy and hard? There is a reason for that. So there are very hard problems, okay, which cannot be solved so easily. And there are variety of easy problems which can be solved fairly easily. So whatever problems we solve with the help of present day computers, they belong to easy problem. And there are some hard problems which cannot be solved by the present day computer, even the best computer available in the world. So they are actually hard problems. So these are the kind of issues which actually motivated people to develop the capacity of a computer and improve the efficiency of the computer and so on. So these are some of the hard problems are one of the motivations to take the subject, like bring the subject into the new domain of quantum computing and so on. Okay, right. Essentially, we get a lot of inspiration from the domain of computer science, and with that, I will also discuss on some perspectives which might be helpful in the context of quantum computing. Okay. So these are the Turing machine which I mentioned. It has 4 main components which we all know. Memory, CPU, program, and read-write device. All the basic operations can be done in this Turing machine. So what we do here are basically basic arithmetic operations and search and so on. Okay. So our present day computer is nothing but a Turing machine. Okay. So there is a circuit model which says that the fundamental unit you have in the computation is the bit, which is either 0 or 1. Okay. And based on this fundamental unit, you also define the operator or gate. So one can have a NOT gate, OR gate, AND gate, XOR, NOR, NAND, and so on. So these are the fundamental gates, and these gates will operate on these zeros and ones. It will give an out. So these are the possible operations you can have. That when you say 2-qubit gates, if the inputs are either 0 or 2 inputs are 0 or 1, these are the possible operations you can have. Okay. And of course, there is only one single input gate, which is the NOT gate. So with these fundamental gates, one can actually construct a variety of a logic gate. Okay. So here I have given a mathematical representation of a general logic gate. A sequence of zeros and ones will be transformed into another sequence of zeros and ones. Such an operation we call it as a general logic gate. So there are some beautiful fundamental theorem which says that any arbitrary logical operation can be decomposed into some of these fundamental gates, and so these gates are important in building up the complex logical operations. Okay, so these fundamental gates are very important, based on which any other operations can be built upon. And of course, there is also practical importance for the NAND gate, which is considered to be a universal gate for various practical reasons, which I don't go into detail of it. Okay. So as I said, there are easy problems and hard problems. So here I have given a simple example of an easy problem. So in an easy problem, the number of operations usually goes as n square, where n is the number of elements in the data set or something. If the number of operations required to solve a problem goes as n square, n cube kind of thing, such problems are called as the easy problems. Okay. For example, sorting out a list of names into alphabetical order. So this is one example of what is called the easy problem or tractable problems. On the other hand, you also have very hard problems. So the hard problems are the one where the number of basic operations required will not go like n to the power, square or cube or something. Rather, it will go like 2 to the power n or 2 to the power n by 2. So please note that the number n is sitting in the exponent. So that means the number of operations are really, really large as n tends to infinity. Okay. So one such example is that given a n-bit number, and you want to know whether the given number is prime or composite. Okay. So if the number is very small, 143, the answer is actually not is very easy, right? So 143 is a composite number. 11 to 13 gives you 143. Suppose I give you a number which is 50 digits or 100 digits. I want to find whether it's a prime or complex, prime or composite. The answer is not so easy, right? So these kind of problems are actually called as the hard problems because the n is sitting in the exponent. So they are called non-polynomial in n. So the earlier one, it's a polynomial in n, and the second one is the non-polynomial in n. So such kind of problems are challenge for the Turing machine or the present day computer. So this actually shows that the present day computers have limitations to solve problems in mathematics. Okay. Right. So here I just want to make a note of some observation about the gates. So the logic gates which I just mentioned, they're all intrinsically irreversible. So what do I mean by that? If you have two input for the NAND gate, the output will be either 0 or 1. If the output of the NAND gate is 1, the input could be either 0, 0 or 0, 1 or 1, 0. Right? So once you have the output, you have no information about the input. So input is once and for all erased. So such kind of operations we call it as a irreversible operation. Irreversible. Okay. Right. So this we can keep it in mind. So information is erased once and for all. Right. And also when the size of the computer becomes smaller and smaller, one also has to worry about the so-called quantum effects and quantum interference and so on in functioning of the electronic devices. So these are some of the issues, some of the aspects which actually inspired us to investigate the possibility of developing new computational methods using quantum mechanics. So is there a way to develop a computer which is not irreversible? Rather, can you have a an operation which is reversible? And can you have a computation which incorporates the quantum effects? So these are some of the interesting questions which led to the subject of quantum computation. So the subject has been developed in similar to the way it has been developed in the computer science. So similar to the notion of bit, here we are introducing what is called the quantum bit or qubit. So I'll introduce the idea of quantum bit or qubit, and I can quickly go through the angular momentum operator, then 2 qubits, and and possibly entanglement if time permits, because I want to cover quite a few things after that. So what is qubit? Qubit or quantum bit is the simplest quantum mechanical system. Why simplest? Because the associated Hilbert space or state space is two-dimensional. Okay. If the dimension of the Hilbert space is 2, we say that quantum mechanical system is the simplest quantum mechanical system that can be thought of as a qubit. Okay. So the capital N is equal to 2. So a general state of such a two-level, we say two-level system of single qubit or two-level system. Okay. So which can be written down as psi is equal to A0 plus B1. Where 0 and 1 are just, earlier I wrote N, right? Get N. I wrote psi is equal to sum over N Cn N, right? So summation runs over all possible values of N. And here we have the summation runs over only 2 values of N. So here this A and B are nothing but our C. So this we can call it as C0, this is equal to C1. So this is the simplest one. A0 plus B1 is the smallest possible quantum state of a cube, of a two-dimensional Hilbert space, and this is nothing but the state of a single qubit. And of course, the meaning of A is inner product of 0 psi, and B is equal to inner product of 1 and psi. Okay. So here the ket 0 and ket 1 are just a representation. Okay. So any two-level system can be thought of as a qubit, and such that A mod square, A and B are such that A mod square plus B mod square is equal to 1. So this term is, this term is similar to summation over n Cn mod square is equal to 1, right? It's the same thing. I wrote the same expression for just two terms. Okay. So this is a fundamental unit of information which is analogous to the bit 0 and 1. So classically, the state can be either 0 or 1, but quantum mechanically, the system can be in a state 0 or state 1 or any superposition of 0 and 1 as mentioned here. Okay. So the same state can also be written down in this fashion. Psi is equal to cos theta by 2 ket 0 plus e power I phi sin theta by 2 ket 1. It's another way of writing the same state. Theta runs between, theta is between 0 to pi and phi is between 0 to 2 pi. So essentially we are writing the state psi in terms of two real variables, theta and phi. Okay. So one can also write the same state psi in the matrix form. Psi is equal to a column matrix A and B. I just write the coefficient A and B. So here A is cos theta by 2 and B is equal to e power I phi sin theta by 2. So graphically, one can represent the state psi in what is called the Bloch sphere. Okay. So what is Bloch sphere? See, according to this equation, the state psi is equal to 0 if A is 1 and B is 0, right? When A is 1, that means A is actually cos theta by 2. When will A be 1? A will be 1 if theta equal to 0, right? And if A is 0 and B is 1, that means the state psi is nothing but 1. The state psi, ket psi is nothing but ket 1. So when will B be 1 and A is 0? So A will be 0 if theta equal to pi. If theta equal to pi, this term will be 0 and this term will be 1. Of course, we can take the quantity phi to be 0, so that ket psi is nothing but 1. So that is what is represented in the Bloch sphere. So here, imagine there is a unit sphere of radius 1. And let's say that the center of the sphere is the origin. Then you draw a vector from the origin to the surface of the sphere. Any point on the surface of the sphere. So this vector can be represented. So this vector is nothing but your state psi. Okay. So as you know, any point on the sphere, on a unit sphere, is being represented by these two real numbers, theta and phi, where theta is the angle of the vector making with respect to z-axis, and if you project this vector on the xy plane, it will make an angle phi with respect to x-axis. That is your phi. So, so in that sense, this point is corresponding to theta equal to 0 and phi equal to 0, and this point is represented by theta equal to phi by 2, theta equal to phi and phi equal to pi by 2. And of course, in addition to these 2 points, you also have a large number of points on the sphere side. So every point on the sphere, unit sphere side, every point on the unit sphere is a possible state of a qubit. You see, it is just a geometrical representation of what I just wrote about. Okay. So in that sense, you have so from this pictorial geometrical representation, we understand that there are infinite number of points on a unit sphere, which means you can think of infinite number of possible states to represent the state of a qubit. Okay. So in that sense, Hilbert space is a big, very, very big place. Unlike the two possibilities, 0 and 1 in the classical case, in the classical bit, the qubit can have infinite number of possibilities. So here itself you see the difference between the classical bit and the quantum bit. Okay. Right. So here maybe the angular momentum and all you might know. So I just want to quickly go through this. So this is one fundamental operator in quantum mechanics, and based on which we are going to these operators will be extensively used in the subject of quantum computation. So you have this angular momentum operator which has 3 components, and these three components will obey this commutation relation, and these components Jx, Jy, Jz, they are actually connected to what is called the Pauli matrices, right? Pauli X, Pauli Y, and Pauli Z matrix. Okay, so these Pauli matrices are basically elementary operations which will be used in manipulating the qubits. Okay, qubits. Okay. So why this angular momentum is important? So here I define what is called the rotation operator. I will explain to you now what it is. So this rotation operator is defined as the e power minus I h cross into j dot n cap phi. So this operator is called as the rotation operator for the following reason. Suppose you have a unit sphere where there is the state of a qubit is actually psi as given over here. Okay. Now you want to go from here to here. You want to go from one point to other point on the unit sphere. So how do you go? One way to do is just by rotation. So that rotation is given by this rotation operator. So this rotation operator, what it does? So this rotation operator operates on psi. It gives you the new state psi prime as follows. So the state psi is being rotated about the axis n cap by an angle phi. And this rotation operation is being executed by this r and phi so that the resultant vector is psi prime. So r operates on psi, gives you psi prime. Okay, where phi is the angle about which you are going to rotate, and n cap is the axis about which you are rotating the initial state psi. Okay. So why this rotation operator is important? So when you are working with a single qubit or two-level system, any arbitrary unitary operation can be written down as r multiplied by some e power I alpha. Any arbitrary unitary operation. So as I already mentioned, quantum operations or quantum evolutions are unitary, or any valid unitary operations are quantum operators. So here we say that these unitary operations which operates on a single qubit can be represented by this rotation operator multiplied by a factor e power I alpha. Okay. So this is how you can build upon variety of unitary operators which operates on a two-level system by appropriately choosing your angle phi and the vector n cap. Okay. So in this way, one can also build up the Hilbert space starting from a single qubit Hilbert space. So suppose you have one qubit which has a Hilbert space H1, two-dimensional Hilbert space H1, and you can also think of another Hilbert space of H2 for another particle or another two-dimensional Hilbert space. You take what is called the tensor product of these two. So the moment you take tensor product of these two, the resultant Hilbert space is four-dimensional Hilbert space. Okay. So in this four-dimensional Hilbert space, this is being spanned by four set of orthonormal vectors, which are 0 from 1, 0 from 1, 0 from 1, and 1 from. So this corresponds to H1, and this corresponds to H1, and this corresponds to H2. So 0, 0, 0, 1, 1, 0, 1, 1. H1 has 0, 1. H2 also has 0, 1. So the combination of all these things, so essentially you have four such set of vectors. These four vectors will form the basis for the resultant four-dimensional Hilbert space. So in this four-dimensional Hilbert space, we can write a general two-qubit state psi as a superposition of all these four. So 0 tensor 0, I just write it as 0, 0. 0 tensor 1, I write it as 0, 1. It's just a compact notation. Simplifying the notation, 1 tensor 0, I write it as 1, 0, and 1 tensor 1, I write it as 1. So any arbitrary 2-qubit state can be written as a superposition of 0, 0, 0, 1, 1, 0, 1, 1. So general state is A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. Where A, B, C, and D are arbitrary complex numbers, but they have to obey this condition. They have to obey this condition, which is nothing but the normalization condition which I mentioned earlier. So whenever you work with any quantum mechanical calculation, you make sure that the wave function or the state psi is normalized. Okay. So in this sense, we can extend this idea for n-qubit system just by multiplying the Hilbert space for every two-level system. H1 tensor, H2 tensor, H3 tensor, and so on up to Hn. And the resultant one is the Hilbert space H, which is the 2 to the power n dimensional Hilbert space. Okay. So this is how one can develop the idea of starting from single qubit. You can develop the idea of the Hilbert space for single qubit to 2 qubit to 3 qubit to n qubit. Okay. Right. So I will skip few of these things because of want of time. Sir, at what time I should finish, sir? Sir? How much time do we have?
Sir, you can carry out the session up to 4:30, sir.
Up to 4:30. Okay, fine. So I will
4:30
quickly.
or 4:15, sir.
Okay, fine. I will quickly rush through the remaining thing.
Okay.
So having defined the single qubit, 2 qubit, and n qubit states in this way by the method of what is called the tensor product of the Hilbert space, now we are going to define the gates or operators which are going to operate on the qubits. So we can classify the quantum gates or quantum operators as single qubit gates, 2 qubit gates, 3 qubit gates, which operates on a single qubit. Okay. So the examples are X, Y, Z, and so on. And we also have 2 qubit gates. Some examples are given over here. Similarly, we have 3 qubit gates. Okay. So I just give you a few examples and I will move on. Okay. So earlier I mentioned about the Pauli matrix sigma X. Sigma X is actually a 2 by 2 matrix, right? As I mentioned earlier, right? Right. So using these sigma X, sigma Y, sigma Z, one can construct any arbitrary rotation operator. And so the rotation operator is actually used to construct any arbitrary unitary operator in the quantum mechanics. So these are the building blocks: sigma X, sigma Y, sigma Z. So you just have to choose the appropriate value of n cap and phi so that you can construct a unitary operator. So the simplest single qubit unitary operators are actually, they themselves are the unitary operators. Sigma X, sigma Y, sigma Z, they are Hermitian as well as unitary, as mentioned over here. You can verify by yourself. Okay. 0, 1, 1, 0. Sigma Y is 0 minus I 0. Sigma Z is 1, 0, 0 minus 1. Now, this sigma X, sigma Y, sigma Z are denoted here as X, Y, Z, or poly X, poly Y, poly Z. Okay. So how are they operating? Let's say this is my X gate or poly X gate. Psi is the input state and psi prime is the output state. So as I said earlier, the quantum unitary evolution can be just represented by either this way or by a matrix multiplication. So this state is actually this, right? Psi is nothing but the column matrix A comma B, and this X is actually represented by this matrix 0, 1, 1, 0. Now you multiply this matrix with AB, you get the resultant one, which is nothing but BA. Fine.
Yes, sir.
Yeah. So what it says that if the initial state is A0 plus B1, the output, if the input state is A0 plus B1, the output state is B0 plus A1. Or in other words, if the input state is 0, output state is 1, input state is 1, output state is 0. Okay. Yeah. If one of them is, if it is 1, 0, it is 0, 1. If it is 0, 1, it is 1, 0. So that's what I mentioned over here. So essentially, it is flipping the state. It is flipping the state of a qubit. Okay. So poly X can be thought of as a quantum gate. Okay. Similarly, you can think of a poly Y gate, Z gate, and so on. And the corresponding matrix multiplications are here, given over here. And if, of course, you can verify by yourself and you can play with other possible gates. So here I have given other set of gates like Hadamard gate, phase gate, pi by 8 gate, and so on. And you will see that all these gates are, of course, unitary. Okay. Because any unitary operator is a valid quantum operation, according to the or evolution postulate. Okay. So these are some examples of single qubit gates. And we can develop further to construct 2 qubit gates. Like, for example, I'm showing an example of 2 qubit gate called C0 gate. So here what happens is that it has 2 inputs, X here, Y here, and output is actually given over here. Okay. So this gate is actually operating on the input in the following fashion. If the state X is actually 0, Y will not be affected in the output. If the state X is 1, it will flip the Y. That is what this operation is. For example, if X is 0 and Y is 0, the output you have 0 is 0 itself and X plus Y. What is X plus Y? Just summation with modulo 2. So 0, 0 here, the output will be, anyway, the output in the first qubit is not affected. Second qubit is also not affected because first one is 0. So 0, 0 becomes 0, 0. 0, 1 becomes 0, 1. And 1, 0 becomes 1, 1. Why 1, 0 is 1, 1? If this is 1 and if this is 0, the output is actually 1 remains 1 here. And here it is 0 plus 1, it becomes 1. So essentially, the 0 is being flipped here because the first one is actually 1. If the first one is 1, it is going to flip the second one from 0 to 1 or 1 to 0 here. And this is actually called as a C0 or controlled NOT gate. Okay. So the corresponding unitary operation is given over here. And this is one fundamental 2-qubit gate in quantum computation point of view. Here we have another example called the swap gate. Essentially, it will just swap the input into inputs. So XY becomes YX. Okay. So that means 0, 0 is unaffected and 1, 1 is also unaffected, but 0, 1 becomes 1, 0 and 1, 0 becomes 0, 1. If this is 0, if this is 0, this is 1. If this is 1, this is 0. Similarly for this. Okay. And this is the corresponding matrix representation of the swap operator or swap gate. Okay. So operator and gate both are synonymous. Okay. And here we develop this idea further to 3-qubit gate. So here you have inputs are A, B, C. The outputs are A, B, and this is A into B plus C. Where this plus is nothing but the summation with modulo 2 operation. Okay. So these are the truth table given over here. The inputs are A, B, C. The outputs are A prime, B prime, and C prime given here. And if you look at here, we can have various possibilities for A, B, and C. So I just give you this zeros. I assign zeros and ones for A, B, C. I have constructed this truth table for which shows for this input, this is the output, and so on. I want you to concentrate only on the third column where C is actually set to 1. So we are setting C is equal to 1. Okay. By setting C is equal to 1, Now you look at this row, this row, this row, and this row. So what is happening here? If the inputs A and B are 0, the output is actually 1, right? A is 0, B is 0, so the product is 0. Since C is set to 1, 0 plus 1 is 1, right? Similarly, if the input is 0, 1, and the output is 1, and if the input is 1, 0, the output is again 1. And I take this as output because anyway, this is not affected, right? And if the inputs are 1, 1, the output is actually 0. So if you look at only the green colored numbers, you see that we are essentially reproducing the NAND operation. Is it clear?
Yes, sir.
Yeah. So we have the unitary operation or a unitary operation or unitary matrix for which we give 3 inputs by setting C is equal to 1. And if you set possible zeros and ones for the input state 0 and 1, A and B, the output is actually the C prime, which is essentially producing the NAND gate. By setting C is equal to 1, this gate acts as a C0 gate, acts as a NAND gate, I'm sorry. And so one can construct a NAND gate from this 3-qubit gate. It is sometimes called as a controlled NOT, CC NOT, or Toffoli gate. So what it shows that since NAND gate is a universal gate from the computer science point of view, so using NAND gate you can generate all kinds of logical operations. So which is being executed purely from a quantum mechanical or a unitary operation point of view. So in that sense, in principle, you can simulate all possible classical circuits from the quantum operations or unitary operations. So of course, we are not developing the quantum computer to do the same job as done by the classical computer. We want to exploit the quantum mechanics to do problems which are hard for the Turing machine or present-day computers, right? That is the idea. Okay, so having given introduction on quantum mechanics and the introduction to qubits and the gates, I just want to, convey few success stories. Few important success stories in the development of algorithms using quantum mechanics, and these algorithms are far superior than the classical counterpart. Okay. So there are many algorithms here: quantum search, quantum superdense quantum teleportation, and prime factorization. I just want to concentrate only on the quantum search. Okay, because of want of time, I'll just search. So here we are going to demonstrate an algorithm based on quantum principle, which will be better than the classical counterpart. So what is the problem here? The problem is the following. Suppose you have a set of element, okay, and this set, from the set of n elements, you want to search one item randomly. Okay, so essentially it's a problem of random search of an element in a search space of n elements. Okay, it is something like searching a name corresponds to a phone number in telephone directory. Of course, now there is no telephone directory. So the telephone directory, the names are ordered alphabetically. Accordingly, numbers will be given. Numbers are given. And suppose if you know the number, you want to find the corresponding name. So this is actually as good as a random search in the telephone directory. So in the best search, you will get the answer in the first attempt itself. The worst search will be you have to go through the entire thing, and the last one will be your solution to your problem. So on the average, you will have roughly n by 2 search you have to perform. classically, you have to perform on the average n by 2 search to solve the problem, right? So this is according to our conventional or classical algorithm, which we have been. Now, how do we approach this problem using quantum principle? And is there any better way of searching this, searching the elements using quantum principle? So the idea is actually the following. Here you have n elements, and you index them, the elements as 0 to n minus 1. So based on the index, we are going to make a search. So I have an index from 0 to n minus 1. I take this n to be 2 to the power small n. So that the index is stored in the n bits, right? You are going to search the index, right? So that index is stored in the n bits. Now, let the input x be an index and define a function f of x such that f of x is equal to 1 if x is a solution, and f of x is 0 if x is not a solution. Okay. So that is how you define a function f of x. So let x be the index register for the problem. Okay. So there is a concept called quantum parallelism due to Deutsch, which says that if you have a register x, okay, you can always construct an operation which goes from x to this state, and you can always find a unitary operation which will go from here to here. Or in other words, you can always find a unitary operator UF or B which takes x to this state. So this operation is a unitary operation. So minus 1 to the power f of x into get x. This is actually unitary operation according to the quantum parallelism of Deutsch. And this operator, I call it as B. And there is a gentleman called Lord Grover who actually gave this algorithm of quantum search, which starts as follows. Suppose if the input state is 0 to the power n by 0 to the power n. What is the meaning of this symbol? 0 tends to 0 tends to 0 tends to 0 up to n terms. Essentially 0, 0, 0, 0, 0 and so on. For the entire 0, 0, 0, I just call it as 0 for simplicity. Okay. Right. N zeros, n bit state. So all the bits are in the state 0. Alpha and what is beta? Alpha and what is beta? So basically beta is a solution and alpha is everything other than solution. Okay. So beta is a solution and solution. Okay. So beta is a solution and everything else other than the beta is the alpha. So I divide the whole summation into two terms. A term which is a solution and all summation into two terms. A term which is a solution and all other thing which is not a solution is the first term. Okay. So we are supposed to transform the initial state supposed to transform the initial state to my solution by appropriate unitary operation. If you don't, it's a real problem. So that's how you do. Okay, so here we are defining what is called the reflection operator. As I mentioned earlier, B. So this B operates on size 0. That gives you B operates on A alpha plus B, A alpha plus B beta. And here, since alpha is not a solution, it will be unaffected, as you see from here, right? F of x will be 0, right? F of x is 0 if x is not a solution. F of x is 1 if x is a solution. So the solution term sign will be flipped from plus to minus. Okay. So B operates on size 0 gives you A alpha minus B beta. In the matrix form, the input state is actually AB, which is the initial state size 0, and the final state is A minus B. And so the operation that A is also a unitary operator. A dagger is I, and the determinant of A is equal to 1. So if determinant of A is, determinant of A is -1. If determinant of a matrix is -1, it is a reflection operator. So here you see that A is also a reflection operator like B. So you have defined two reflection operators A and B. And using these two operators, you are going to define another operator called G, which is the multiplication of. So if the initial state is G, if the initial state is size 0, you are going to apply this AB on that. And first B is operating on size 0, that gives you size 0 prime. Then A is operating on size 0 prime, that will give you psi 1. So basically, psi 1 is the final state after one application of the operator G on initial state size 0. Is it fine? Now you can do the entire calculation just with the simple matrix multiplication. In the matrix form, this is my A, and this is my B, and this is my size 0, and this is the resultant simplified into this thing, which is nothing but psi 1. So psi 1 is essentially 3 cos 3 theta by 2 alpha plus sin 3 theta by 2 beta. Okay. So what is cos 3 theta by 2? Cos, which is nothing but cos theta by 2 plus theta into alpha plus sin theta by 2 plus theta beta. Okay. So this is my psi 1 after one operation of the operator G. Okay. G itself is a product of two reflection operators. Right. So now you keep doing this. Similarly, you construct psi 2 by applying G on psi 1, and you construct psi 3 by applying G on psi 2, and so on, and you keep applying up to for k times. Repeat the application of G k times. So you'll get the final state something like this. Now the question is the following: operation, at what level I will be getting the final solution? That means, so what is the solution? The solution to the problem is that upon repeated application of G, I should get the state. I should get the final state to be beta, which is my solution. So essentially, you're asking the question: how many times I have to apply the G so that psi k becomes beta itself? Okay, beta is my solution. Alpha is not my solution, right? So beta is my solution. So what you do is, if psi k is approximately equal to beta, you have to set this term, the theta by 2 plus k theta, approximately pi by 2. So only under this scenario, this term will vanish and this term will be 1. So you have psi k is nothing but beta. So which means k is approximately pi by 2 theta minus 1 by 2. And here you see that sin theta by 2, which is sin theta by 2 is actually 1 by root n. Okay. Since n is very large, sin theta by 2 is very small. So sin theta by 2 is very small because n is very large. So since sin theta by 2 is very small, which can be approximated by theta by 2. So theta by 2 is approximately equal to 1 over root n. Or in other words, if you set theta is equal to 2 by root n here, the k is actually given by this. K is given by pi by 4, approximately equal to pi by 4 square root of n minus 1 by 2. If you ignore this factor 1 by 2 because n is very large, essentially k is pi by 4 square root of n. Or in other words, k is approximately square root of n. In other words, if you apply the operator G, square root of n times on the initial state size 0, the resultant state is the beta, which is nothing but the solution of your search problem. So the order of application of your operation, it goes like a square root of n, not as a n itself. or n by 2 itself, as in the case of classical search algorithm. So in that sense, this particular algorithm gives you a search problem. So definitely this algorithm is, much more efficient in principle compared to the classical search algorithm which we have been using. So this is one such demonstration where the idea of superposition and the unitary operation are useful. They're very cleverly used to reduce the number of operations to get the solution to the search problem. So this is what I have just shown here. This is your alpha, this is your beta. Now the initial state is psi 0. So psi 0 is being reflected by P, you get psi 0 prime. Psi 0 prime is further reflected to get psi 1. So essentially, upon application of A and B, psi 0 actually goes to psi 1 upon one operation of G. Upon applying this G operation K times, the final state will be approaching towards beta. When we apply G K times, K is roughly of the order of square root of n, you will get the final state closer to the solution beta. Sorry. So essentially, the number of operations required to get the answer for the search solution is square root of n according to this particular algorithm, which exploits the unitary evolution, the unitary property evolution, and the principle of superposition. So this algorithm was given by Love Grover in the year of 1997. So it is one such story where you see that quantum principles can do more efficient computation than the classical counterpart. So with that, I'm going to close my session because the time is really running out. There are other interesting algorithms, which again, supremacy of quantum algorithms compared to the classical counterpart. There are possibility of developing very powerful algorithm using quantum principle for the prime factorization, which I said is one of the hard problem. And this algorithm was given by Peter Shor in the year 1997. Okay. Of course, there are a lot of activities are going on throughout the world, contributing theoretically the classical computer. So at least in principle, it is the case and the classical computer. So at least in principle, it is the case, and it is the the option. The hopes are alive. The hopes are alive to demonstrate that what we show theoretically will happen one day experimentally. There are lots and lots of hopes and possibility. I think more youngsters and people. I think more youngsters and people who have interest in quantum mechanics have to come together to give new ideas to take the subject forward to realize the quantum computer and so on. So with that, I just close the session. There are some references. Probably you can take it up. You can read further to create more interest to the students and in your circle. With that, I once again thank the opportunity given by the Bapatla Engineering College for having a wonderful interaction. Wonderful sessions of sharing my thoughts on quantum computing with a good number of participants from all over the country. Thank you so much, and I'm very happy to take up few questions before we close the session. Thank you, sir.
Thank you, sir. Thank you very much, sir. Thank you, sir. Thank you very much, sir. You cover all the fundamentals of the quantum mechanics in a very detailed manner, sir. And computation and algorithms are really big concepts. It will take much more time actually, but you have explained it in a very simple and style in a very short available time. Thank you very much, sir, for taking the session. Now it is time for the questions and answers. So the audience are requested to raise your hands to ask the question directly, our resource person.
Sriram sir. N. Sriram sir.
See, sir, please ask the question.
Sir, Sriram sir. Are you able to listen, sir? Sriram sir. N. Sriram sir.
Sriram sir. Are you listen? Okay, any participant wish to ask a question, please raise your hand. Okay, Lakshman Rao, sir. Your mic is allowed. Sir, please ask your question, sir. Lakshman Rao, sir.
Sir, mic చేశాను మీకు.
Sir, mic రావట్లేదా?
మొదట్లో పెట్టుకోలేదు.
ఇప్పుడు చూడండి సార్. Sriram sir, ఇప్పుడు చూడండి. President. సార్ ఇప్పుడు వచ్చింది చూడండి సార్ ఒకసారి.
Sir, some other also raise the hand, sir. Suresh Sangati.
Hello. Hello.
Suresh,
Hello, sir. Am I audible?
Yes.
Yes, audible, Rama.
Suresh.
Sir, good evening, sir. Good evening, sir. Sir, now my question is related to the quantum teleportation, sir. Shankar Narayan, sir. Hello.
Sir, please proceed.
Sir, my doubt is related to quantum teleportation. So, according to the no cloning theorem, it is not possible to copy any arbitrary state, sir. But with the help of entanglement, it is possible to send one arbitrary qubit to another person. My question is, once we send the qubit to the other person, can we have the same qubit with me also, sir? Means, can I able to send the same qubit to another person after some time? Is it?
There are two people, A and B, who are sitting far away. Okay.
Yes, sir.
And now A wants to send a qubit kit psi to B.
Yes, sir.
Now A is actually doing some manipulation. Then with that manipulation, he actually he is doing some unitary operation. Then after the unitary operation, he actually sends the result of his measurement to B. Right?
Means he lost that qubit.
Exactly. He does the measurement. Once the measurement is done, actually the state collapses, right?
Okay.
And you have a final result of that. That result is actually being teleported to B. And using that information, he is actually reconstructing the
Yes,
qubit
sir.
on the other side. Yeah. So
Yes, sir.
it is disappearing from here and appearing there.
Means
So
it
you
is
cannot-
only one side, and means it is only possible to send one qubit to only one person.
Exactly. One qubit to one person. Yes.
Not possible to send some 10 persons at a time simultaneously is not possible.
Yeah. I mean, according to the algorithm, it appears to be not possible because you cannot have a cloning. You cannot
Yes.
have a copy of it.
Yes,
So
sir,
one
yes, sir.
qubit can be sent to one person. Correct. According to quantum teleportation algorithm. Correct. Yeah.
Okay, sir. Okay, sir. That is my doubt, sir.
Okay.
So maybe and it is also, it means it is like a barrier for the communication. It is not possible to communicate with all at a time. It is only possible to communicate with only one person with the entangled state.
See,
Am I right, sir?
yeah, as you rightly pointed out, we cannot repeat the state. We cannot copy it.
Yes, sir. Okay, sir.
So copying is not possible. And as you rightly pointed out, that could be one disadvantage of sending information simultaneously to many people.
Okay, sir. Okay, sir. Thank you.
Yeah.
Sir.
Yeah.
Sir, one more question, sir.
Please.
In superdense coding also, we are sending 2 classical bits with the help of entangled state.
Yeah.
Is it possible to send more than 2 classical bits, like 10 classical bits or 100 classical bits? Is it possible, sir, with one entangled qubit, or only 2 classical bits?
1 minute. Actually, it's what reverse of it is a teleportation. So both
Yes,
are
sir.
actually equivalent and complementing each other. So that also the same thing is applicable. I don't think it can be sent to.
Not many people, sir. My question is, we can send 2 classical bits with superdense coding.
Okay, you want to extend the idea of single key.
I want to send 3 classical bits or 10 classical bits.
I understand the point. Yeah, so it should be possible. I think people might have worked on it, but I'm not sure about it.
Okay,
So
sir.
what is done what is done in superdense coding is transferring one qubit from single qubit from one place to other place by a classical channel. One can also think of sending many. Yes. So people might have done it, but I'm not sure about it. Yeah.
Yes, sir.
And if people have not done it, I mean, you can try it out. I think that's an interesting extension of superdense coding. Yeah.
Yes, sir. Sir, the last question, sir.
See, or in other words, you can do it, parallelly, right? Suppose you have 2 qubits.
Yes,
Every
sir.
qubit you apply a dense coding, right?
Okay, sir.
So yeah. Okay.
Sir, the last question, sir. Quantum
Sure.
interference
Yeah.
means I understood that quantum interference is the technique. For this technique, we get the correct answer. Means they constructively interfere and gives the right answer. And all destructive interference like
Okay.
things that I read in the books, but I didn't understand correctly. Just give me some explanation, sir. Quantum interference.
Actually, there is something called quantum error correction, right? There are
Yes, sir.
principles called quantum error correction, where they make use of this error correction such a way that they tailor the interference such a way that the interference actually helps for your communication purpose instead of destroying it. So I presume it's basically quantum manipulation, wherein the interference is basically coming from the idea of superposition. So you give a condition such a way that the interference always helps rather than destroying the information. Yeah. So, but that's again a separate kind of domain of activity, which I do not know much about the quantum error correction. But this is the idea. I mean, it's always possible to do the error correction in such a way that interference is helping you, not the other ways. But again, it's a very tricky thing. Yeah. In general, interference actually destroys the quantumness. In some cases, one can cleverly manipulate the interference for your advantage.
Okay, sir. Yes, sir.
But not always, yeah.
Yes, sir. Yes, sir. Okay, sir. Thank you, sir.
Yeah, thank you.
Sir, good evening.
Sir, Suresh Sangati.
Okay,
Yeah.
sir. Good evening, sir. Good evening, sir. Am I audible, sir?
Yes.
Sir, first of all, I express my thanks for giving such a beautiful narration. Sir, my question is, what are the areas where the quantum computers are influencing now, are used?
See, as
Which
per,
areas are using quantum computers nowadays, sir?
sir, as per I understand, there are a lot of progress from the theoretical point of view.
Sir.
Okay. And mathematically and theoretically, people have got very many, interesting results and so on. That too for few qubits and so on.
Sir.
Okay. But developing quantum computer in the large scale and implementing to solve certain problem, that I'm not sure how far we have reached. Though the Google and IBM, they claim that they have designed quantum quantum mechanical based chips, but I'm not very sure how far they can be extended to large scale computation and wide applications and so on. So the applications are many, but the question is, how do we realize it? Because we are talking about manipulating the atomic state, which itself is a task, and it is also going to be a very expensive affair in some sense.
Yes.
But the question is, can we make this whole, methods cost effective? Those are all some of the concerns in designing the quantum computer. Yes.
Okay. Thank you, sir.
Yeah.
Sir, good evening, sir.
Sir, Lakshmana, sir.
Yes,
Sir.
please.
Sir, very interesting, sir, this session. But
Yeah, thank
I
you.
got one doubt. And what is the quantum mechanics effect on materials? Maybe a revolutionary level, maybe materials behaviors and all changed it, sir, but due to this quantum mechanics. Small doubt.
Sir, actually, first of all, already whatever you see, the properties and behavior of the systems, they are all quantum mechanical only. For example, the magnetism. No, we have, we are familiar with the magnetism, right? Magnetic properties and so on.
Sir.
And then the magnetic properties themselves are being explained only with the help of quantum mechanics. So only thing is that what we see is actually the average behavior of all the atoms and so on, collective behavior.
Sure.
What we observe in the laboratory is the collective behavior of all the atoms and molecules. And those collective behaviors are being explained only with the help of quantum mechanics. So already quantum mechanics is there in our observations and results and so on. But the problem is, how do we manipulate the individual atom and individual atomic states? If you are able to manipulate the individual atomic states, you can do very many interesting things, which are the whole challenge actually. Yeah.
Okay, sir. Okay,
Yeah.
sir. Thank you, sir.
Yeah. Magnetism itself is a quantum mechanical phenomenon. Yeah.
Phenomenal. Okay.
Sir, please, if any other participants wants to ask questions, can raise your hands. Otherwise, the session will be closed. Anil, sir.
Sir.
Sir, please conclude the session, sir.
Okay, sir. So it's a very wonderful session. Shankar Narayan sir covered all the big concepts in a very short time. We are very happy to hear the fundamentals, all the fundamentals which are covered during the session. In a very short time, that is important. So it will take much more time actually to explain all the algorithms and computations, logic gates, these things. But in very short time, in detail, they are explained by our resource person. Thank you very much, sir, for taking the session. The successful, fruitful session is we have also heard about. So now it is a time to say the vote of thanks for the resource and our participants and the management and other. I now invite Mallikaran sir to propose the formal vote of thanks to our resource person, other dignitaries. Markal sir, please take the session to express your vote of thanks.
Okay, good
Thank you,
evening,
sir.
sir. Sir, I'm SLV Mallikarjun, Assistant Professor, Department of Physics,
Okay, sir.
Bapatla Engineering College, Bapatla.